Let's do another hour and a half. So today I'll do, instead of two 45-minute rounds, just do one 1.5 hour round, and I'll just try to work through as many of these as possible. I think these are much larger circuits because of the name. So I'll just work on it one by one as opposed to opening a lot of tabs, because then with smaller questions I save time not waiting for the simulation, but I'm not going to save much time with these bigger problems. So let's get going. Perhaps I'll just copy and paste this here so that I can more easily see the description of the problem. And yeah. Active low synchronous reset. So that's one spec, that's done. When the reset signal is deasserted, then after the next clock edge, so I want to see if I see. Why don't we do this then? Check a text message. Okay, all good. Case state and case. So I start at A, which is like at reset. So this really just wants to go to like after a reset. And so for one clock cycle, so at reset, I really want to go to after reset, right when we after reset the next cycle. So next clock edge, I guess I don't know if it's like neg edge. That would be kind of complicated. We'll see. I'll just assume pause edge as opposed to next clock edge, the FSM has to assert the output F to 1 for 1 cycle. So here, next state will go to, when we deassert reset, we'll go to after reset for a cycle. Then I have to monitor the X input. So notice we stay in this cycle for only 1 cycle, and then so if state equals after reset, the F is only asserted for a single cycle. Then the FSM has to monitor the X input, specified by this mon X situation. And when X has produced 101 in 3 successive clock cycles, then G should be set to 1 the following cycle. While maintaining G equals 1, FSM has to monitor Y output. If Y has the value 1 within at most 2 clock cycles, and then mon Y. So after we monitor X, we monitor Y, and then when we reset, we go back here, and then we start at this 1 output anyway. So monitor X says one clock cycle, let's just do a stream. So we put it in LSB, which means we pop the MSB, like so. And when we transition to monitor X, so we're here for 1 cycle where we assert F, but right after we're going to monitor X. So if X is like this, then let's say 101, then this becomes 101. Should set to 1 the following clock cycle. While maintaining G equals 1. I must maintain G equals 1, okay. So if I detect 101, my state's gonna be at monitor X. So next state, as soon as I detect, then my next state will be monitor Y, otherwise stay in monitor X until I see this. And keep in mind that stream X won't be 101 or it's not possible unless it's in this state, because otherwise we're always 0. So we go to this state, and then we start monitoring input. So if we're 1, 0, 1, 1 being on the third cycle, then the next cycle we monitor Y, and then on the third cycle, yeah, set G will happen on the third cycle, but we need to assert G on the fourth cycle. So then actually delay this by 1 cycle. Okay. One permanently. So when we're in monitor Y, we basically have 2 cycles for Y to become 1. And if it is, G is 1 permanently. And if not, then G equals 0 permanently. So I just have a saturating count. Whereby if the state is monitor Y, then sat count and so this will only go up to 1. So this is saying if I'm in this monitor Y, I'll count from 0, 1, 2, 2 being the saturated count, and 2 forever not ever going to clear G. Or it'll clear G. And so count from 0, 1, 2 because of this, and then it'll stay at 2 because of this. And if I'm not in this state, then I'm just at 0. So basically, don't touch anything until I want to clear it. So assign clear G is when state equals monitor Y, and there's no state transition from monitor Y other than to reset, which is because of this. Just to be more explicit, we always just stay here. So if I'm at monitor Y as my state, and then I've made it to, so I start at 0 and then inclusive 1 would be 2 cycles. So this is the second cycle, and this so I'm here, and in these two cycles, in either of these two cycles, I need some state element because this is across two cycles. So maybe I just do this. It's easier. This is 3 bits plus 2 bits, and yeah, I do need this actually. So this is the same as before. I'm in this monitor thing, and if it's not 2, I add it up until it becomes 2. And so this would be 0, 1, and then the third cycle would be 2. And then so by the same token, on the third cycle, it'll stop flopping it. On the first 2 cycles, it will shift the Y's in. So suppose Y is 0, then next cycle stream of Y is 0, 0. And then suppose next cycle is 1, then it'll be 0, 1. And count is 1. And then stream Y gets propagated to 0, 1 when count 1 Y is 2 on the third cycle. So we can do the calculation on this cycle. If this requires this clipping of Y to take place in the same cycle, otherwise it can take place in the next cycle. So for 2-cycle window, allow for the streaming to happen, and forevermore, I'm just gonna keep stream Y, and if I keep stream Y, then I can just reference against stream Y to know whether or not Y should be asserted or not. So I would want to clear, so if I do nothing, then this set G will remain 1 forever, because I set G and then this maintains it, so as long as I don't clear it, G is maintained as 1. But now I can say I want to clear it if and stream of Y equals so the 2-cycle capture, they're both zeros. We're at the 3rd cycle and we didn't observe stream of Y being 2-bit 0 in the past 2 cycles, and we're stuck in this state as a qualifier, so I think this should be okay. Maybe we just run through this again just to double check everything. So when we reset, we stay at state A, and if it's the asserted, at the next clock FSM outputs F to 1. So right after reset, we have this going to after reset. So 1 cycle after reset, we're at after reset as my state. So we do this for 1 cycle, and we do this for 1 cycle because our next state will immediately jump to monitor X. When we monitor X, we need to make sure that we need to wait for this X to provide a 101 value, which is described here if we're in state X and we shift in X. We're just going to keep shifting in X until we detect a 101, and then and obviously we need this filter of this state. And then so when we detect this, we're going to set G on the following cycle. And then actually this, right, because if I insert a 1 here, then this is the following cycle, and then this would be 2 cycles after. So actually, we want this just to be next stream X. Next stream X, where I would assign next stream X as just this. So 1 is inserted this cycle, and then the next cycle transferred here would then go ahead and set the G as 1. This will hold it forever. And then if Y has value 1 within 2 cycles, it will remain at 1. If Y does not become 1 within 2 cycles, it will become 0 permanently. Because of this motif, this G transferring to G every single cycle, we basically don't have to do anything to maintain 1. So all we need to do is just basically check for this case if Y doesn't become 1 within 2 cycles, which is handled by this stream of Y. So stream of Y is just going to have this state filter, and this state filter says in cycles 0 and 1, I'm going to stream stuff, and then on cycle 2 or the 3rd cycle, I'm not going to stream anything. So this will capture for 2 cycles, and then if I'm at cycle 2, whereby this guy says I'll count from 0 and then 1 and then 2, and then if I count it 2, I'll just be stuck at 2. Unless I'm not in this state, then I just default to 0. Because we get this guarantee from this count monitor y variable, we'll be kind of stuck here forever, and then the stream y will pass to stream y. Now the last thing to do is that if y doesn't become 1 within 2 clock cycles, then FSM should set g equals 0 permanently. I assume this means next cycle. So that's how I implemented it, but if not, I can just do the right-hand side instead of left-hand side, for example. So clear says if actually, let me think. Yeah, this needs to be an extreme y, actually. And the reason is because if we're here, we are active on like count equals 0, count equals 1. But the issue is at count equals 1, we're already at the second cycle, so then we have a cycle delay to stream y. If we check stream y here, then that means 1 cycle later you would have this information, but then clear the clear g and g happens 1 cycle later. So then you could basically have a case where, well, you would have a case where count is 0 and then count is 1, and the next cycle you're supposed to deassert g. But then if you had stream y, then you add an extra cycle. It's only 1 cycle later on the third cycle you do this, but then since clear g adds another cycle, you can't do that. So you have to use an extreme y to be able to anticipate. So for example, in the second this actually. So 0, I would have this value, and then when this value is 1, this would have the previous value, and then this would have the new value. And then at 1, I'm already at the second cycle. And then if I'm at 1 and the extreme y is 0, that means on my second cycle, I have yet to observe any y. And then I want to set g to permanently, presumably on the next cycle. So then this is satisfied, the second cycle is satisfied, we haven't observed any y is satisfied, we cleared g. Clear g 1 cycle later says g is cleared permanently. We'll never set g again because we'll be stuck in monitor y state. And yeah, let's give it a shot. Post reset's not really used, right? Set g, clear g's for the set hold reset of g, and Yeah, so here the mistake was same as the other sort of like delay mistakes. So here, if I take if I take stream of x is 101, there's an extra cycle delay, which is why the g was a cycle longer. So in this case, you know, if in this cycle we have a 1, then we already know next stream x is going to be 101. And because G is asserted for 2 cycles, as soon as we go to monitor Y state, G is asserted for the first cycle already, so we can't afford a delay here. So as soon as we detect it, the G will have a 1 cycle delay, and then the G will be asserted first when monitor Y starts, and then when monitor Y starts, the rest of the logic kicks in, and then we're done here. Okay, so this is done. Series of 5 exercises, God. I don't get why this says data is shifted in MSB first. This says otherwise. You're at 0, you do 1, and then it keeps shifting 2, which means you shift it in the LSB, and then 4, and then 9. So all right. mega-FSM that searches for 1101 in the input stream. Okay, 1101 like this. So which would be most convenient? I want to shift it in LSB, so because 1101 means 1 1 0 1. Then I can just check this without reversing it. And then this has a 1 cycle delay of when it actually happens, which is fine. You could make, you can imagine making this and this a separate variable. Forever. Just hold it so it's forever. So I set it and I don't have a clear. So it's forever until reset, which this happens. 0, 1, 2, 3. Four forever. Proper bit pattern is detected. So this says after reset I do 4 of these, and after reset I do 4 of these. Otherwise, don't care. Oh, I see. So the fourth one, we start piecing everything together. Started when this is detected, so is this problem so this one detects 1001, 1101. Shift in 4 more bits to determine the duration of the delay. So then I think this is this one, and then wait for the counters to finish counting. Ooh. Which is, I guess, new inputs. Okay. And notifies the user and waits for the user to acknowledge the timer. So like a valid ready, okay. In this problem, implement the FSM that controls the timer. until done counting is high. At that point, the machine goes to another state, must assert done to notify user, and waits until ACK is 1 before being reset to look at the next occurrence. So back to this original state. State machine should have a reset into a state where it begins searching for this. Here's an example. The X states are confusing. They might indicate as don't care, for example. So I don't get why this says just implement the finite state machine that controls the timer. Obviously you need everything. So we have states of detection, shifting, wait for done, and notify. So shift for 4, wait count, and wait ACK state, next state. I know you can't see it, but yeah. So this just finds 101. And by the way, some boilerplate code, and data is just data, and if I reset, So 1101, it starts shifting the cycle after. So here we start shifting the cycle after. But the thing is, I want to transition to this state. Unless I can say this is the same state. Then maybe that's easier. I feel like I need to insert it here and then I get the 4 cycles. So yeah, I want to do it like this. So here I want to just go to the next state. And having a separate state can help me ignore a lot of the other variables and isolate this problem into smaller chunks, so it's a lot easier. So okay. So this identifies this one, so I want the next cycle to go to shift 4. Actually, let me just make this window smaller so you can see it. Otherwise, they detect, right? We just want to keep detecting until we detect 1101, and then the next stage is, or the next state is shift 4. When we're in shift 4, so we reset this when we get out of the detect state. So when we're in shift 4, we're just waiting for this to tell us when it's done. 1, 2, 3, 4. Just to prevent the annoying text movement. Shift 4. So when here and here, so at this cycle, we trigger this in the next 4 cycles, which is start shifting and state equals detect. The next day after, when this happens, we're already in shift 4, so all good. And shift enable is shift enable, which is this one, so all good there. And the reset will only happen at this state change, namely detect to shift 4, so bang, bang. Otherwise it won't happen. I also want to expose 0, 1, 2, 3 to count here and say final count is just going to be a 3-bit counter, and I just want the actually I just want final count to be a 1-bit thing, such that I can say if final count, then namely this specific cycle, then I want to do wait for count, otherwise stay in shift 4, whereby final count is just going to be if so 0, 1, 2, 3. Then, right. So final count will always only trigger here or here, and then the next cycle we go on to the wait count. And wait count is just going to do assign counting equals 1. Maybe here is a little bit easier to read. Okay, and if I get this done counting, then the next state is wait ACK, otherwise I'm at wait count. So if I'm not done counting, just keep staying here, otherwise if I'm done counting, the very next cycle I get out of this, so then the next cycle, but not the same cycle, is done counting, so we can have the handshake, then done counting and counting, basically done counting and stay equals wait count, like here. Then we'll go into the next stage. And very similar here, we're going to say yeah, this is wait for done counting input. And this will be asserted for the duration of this state until we get this ACK handshake. So here, and ACK means we'll go back to detect, otherwise just wait for ACK. So more specifically, done and ACK is, done is this state, so this state, and ACK will next cycle go back to detect. Otherwise we're staying, we'll wait ACK. And then here's an example. So when we're at wait, so if we ACK, we go back to detect, and when we go back to detect in this cycle, reset is released. So state equals detect, right? And there's no reset. And we'll start storing this data. And yeah, it should be good there. Let's see. Well, this part hasn't been weaved in yet. Line 33. One, two, three, four, and then here's 1, 2, 3, 4. 1, 2, 3, 4. Let's try again. 42. Oh. Oh, because it used to be here. Okay, whatever. Yeah, it's a difficult part of Verilog. There's a lot of places for you to hit. So reset is what starts the shift enable. And I'm only if this happens and this happens, only if this happens. But if I'm at reset, then start shifting should always be 0. So why is shift enable as 1? Shift enable is 1, and shift enable is 1 here. That means shift enable is 1 here. That means in this specific application, the actual reset causes it to start. The application's different because I want the last reset to trigger for count as opposed to just overlapping. Yeah, I can tell this will take a long time. The shift enable if reset is 1. Oh, I see. The submodule they had us build is like completely different than what they need in this problem. Can I just do this? So reset forces this to be 0, and then it'll keep forcing it to 0 until here, and here like detect and start shifting. So here would be the last cycle of my reset. It'll deassert here, and there'll be no more reset. So 0, 1, 2, 3. So no more reset, and 0, 1, 2, 3. Let's see how far I get on this one. Okay, I think I just need to rework the shift 4 module completely then. Reset really means start counting. So my plan is like reset until here. So this stops reset. Stopping reset. Actually, I don't need to do all this then. So reset is always 1 unless we're doing the state transition. So if reset's always 1, this is always 0, and then if we do the state transition, then the next cycle starts. And when the next cycle starts, we're going to count from 0 to 3. Start counting, and which sets this, or hold the previous value, and I want to clear it if the count is 3. So suppose I start, the next do count is 1, and so when count is 3, it'll take 1 cycle to propagate do count to 0. So when count is 3, we'll have count is 4, and then do count will be 0, and we'll be stuck at 4, which is good. Yeah, I feel like I could have just done this instead of all this, but whatever. So when I start, which is the state transition, next do count is 1. So I won't start counting yet. So the next cycle, this is still 0. Here is 0, and then 1, 2, 3, 4, and then it's stuck. All right, let's Oh, actually, it's okay. So here it's saying the shift enables one cycle too late. So here's 1101 detection. And if 1101 detection, this is asserted. And then what's reset? Reset 0, cool. And then this goes into here. So start is asserted. When start is asserted, next do count is asserted. If it is 4, then I just want to be 4. Otherwise, if my do count is off, meaning well, I don't have to do that. I want to have proper reset. So it's reset or if. Because otherwise the counter's like starting at 4 and then it needs to wrap around, which could cause issues. Okay, so now we have this issue. So my final change here is to make sure that instead of not detect, because if not detect resets it, yeah, then we'll reset it right here as soon as we transition. But I know that when I go to the third state, this is done. So then I'll just reset it after this state. Okay, so 5 minutes. The complete timer. What is this? Waits for the counters to finish counting and notifies the user. So for 4 cycles, I'll take some shift in the next 4 bits of what, though? Data? It has to be data. Okay, after that, the state machine asserts its counting output. To indicate its counting, state machine must count for exactly delay 30 plus 1 times 1,000 cycles. Means 6,000 cycles, okay. Here it's 1101, and then we have 0001. So 2,000 cycles. Okay, when circuit isn't counting, the output is don't care. Okay, so counting is a qualifier. So 1101, you do your 4 cycle thing, and then after your 4 cycle thing, you have this stream of 4-bit data, which determines this bottom counter, and you assert counting as long as your counter is counting, and then there's something with the count 30 that's not clear yet. At this point, the circuits must assert done to notify the user as usual, and then wait for act. Circuits must reset to a state. Well, what's supposed to be count 30? 1101, and then you have 1110. This should be equal to delay for 1,000 cycles, then I see. So every 1,000 cycles, this counter goes down. Got it. I think I'll 1, 2, 3, 4, 5, 6. Since this, yeah, I might save this for tomorrow. It's not. Well, I guess I can try for like 20 minutes. See what happens. This actually seems simpler than this problem to an extent. So it's 342. I'll do this till like 4. So there is still because these series problems are like, I don't necessarily want to do it for like spread it across 2 days, because I don't want to, if you refresh, all the code is gone, basically. That's the issue. So I still need to detect it, I still need to shift something in for 4 cycles, and then I still need to so previously the count is like after the shift enable. So here, oh no, yeah, it's data here, and then 1101, and then I shift in 4 things, and then I go ahead and start my counting. So I just need to modify that to shift in 4 things when I'm at shift 4, but then let me copy the submodules as well. And so if I'm at shift 4, which window am I on? Okay, here. If oh, I see, that's why. So you want to shift in stuff. So if I'm shift 4, when in here, I'll shift 4, and after this, I'll know how many remaining I have in thousands. So this can be my count 30 actually. And I'll decrement it by 1 after every 1,000 cycles, which I believe I had somewhere. Okay. Let's make sure this is correct. Okay, good. I guess I don't need this anymore, so basically I want to (0 to 99) a cycle after reset. So the next state is wait count, then I'll start the count in the next cycle. This would mean that it's the 1,000th cycle, and I'll just keep decrementing it. And then ergo, if this is 99 and I'm in state wait count and my count is 0, then I can transition into the done situation. And count equals this. Then I'm done counting, and then next day is wait ACK, and then ACK does, just resets it like in the previous problem. So let's just fix all the compile issues. I'll just use the final count for that anyway, as opposed to shift enable. So I can just comment this out because the final count works anyway because of the previous problem. Why is this happening again? 100. Two 2004 cycles. All right. Yeah, this is like, they made this problem kind of impossible to debug. We know from the previous problem, shift 4 should is 4 cycles. And more specifically, shift 4 is 1, 2, 3, 4. So I think at least that's right. One thing is, it's the value for count is legitimate on weight count only. So where do I use count? Okay. If the next state is weight count, which means I am at this cycle, then I want to start counting. So 0 to 999, 999 would be the thousandths. 2004 cycles. But there's no diagram for that. There's only a diagram showing this. So 2004 can't be, this only happens 1,000 cycles, right? So this is saying I'm counting 4 more cycles per 1,000. So this would be 1 after shift 4, and my state will be wait count, and my 1000 counter is 0. So this is 999 and wait count. Then next cycle, this will be a 1. This one actually goes on for like kind of too long. Actually, this reset is I want this, don't I? So when this says I'm going to wait count in the next cycle, then I release it. So next cycle is 0 all the way up to 999, and then you're going to go ahead and do this, and this will stay in wait count for a while. So reset will be 0 for a while, and then this will keep counting 0, 999, and then when I get to 999, this will decrement this by 1. Let's see if I get closer here. Okay, that's quite a bit better actually. So this prematurely says 0, so perhaps but I don't get why that would be the case then. So great, I solved this super duper complicated problem. Why state instead of next state? Here next state is blah and state is blah. So if state is wait count, then reset goes to 0. Oh, the next cycle it's 1 already, so we do get 0, 1, 2, 3. I see. I thought the first cycle after reset it's 0, but I thought I had to somehow reinforce this 0, but after reset it's already 0 because of reset. Okay, so all done here, and yeah, the next sessions of hardware I'll probably just finish these off. Probably not these because I don't think they'll ask these, and probably not test benches because I'm not trying to be a verification engineer. All right, that's it for this one.